So, multivariable calculus. We're talking about things like this, a surface. Up till now, everything we've been talking about in calculus has always been in two dimensions. So we have one input variable, an x, you put into the function, and a y comes out. Y is the dependent variable because it depends on what x you put in. You can pick any x, so x is independent. Well, you can pick any x that is in the domain of the function, and you get out any y that is in the range of the function. So our example, y equals x squared, a parabola. We're good with that. The domain, you can put in any x's because you can square any number. Really, what can't you do? Well, don't divide by 0, don't take the square root of a negative number, don't take the natural log, the ln of 0 or a natural number. Those are basically the things that we would worry about. As long as your x doesn't do that, then you can put it into the function. So let's extend that to then 3 dimensions. So what we're upping is, because right now we've got 2 dimensions, one's an input variable, one's an output variable. If I go to 3 dimensions, so up this to 3D, now we're in multi-dimensional territory. What we're adding is another independent variable. So I've got 2 input variables, I've got 2 independent variables, x and y. I pick x and y, and I've got one output variable, one dependent variable, the z, let's say. So z is a function of x and y, just like here y was a function of x. And now if I think about this function that I have here, z is equal to x squared minus 2y squared, you pick an x and a y, okay, it has to be in the domain of the function. We said don't divide by 0, there's no dividing by anything here, so you're fine. Don't take the ln of 0 or negative number, there's none of that, so don't worry about that. What else? Don't take the square root of a negative number, no square roots. So that's a polynomial, that's a polynomial. We're just subtracting 2 continuous functions, the x squared and the 2y squared. It's a parabola and an upside down parabola. The 2 makes it a little bit skinnier. Anyway, long story short, the domain would be expressed in sort of lay people's terms. I can put any x and y pair in there that I want. Expressed in math terms, it's all of R2. You can pick any xy point. And what comes out? Well, it depends on what, the z comes out, but what value is z? The height of the curve, let's say, it depends on what x and y you put in. If I make x equal to 0 and y equal to 0, then z is equal to 0. So the origin, 0, 0, 0, is on the function. This surface goes through the origin. This is the surface that I was talking about here. Now I can see an upward-facing parabola. Yeah, that's the x squared. And if you choose a y, pick any number, plug it in for y. If I make y equal to 0, then z is equal to x squared. So everywhere along the y equals 0, you're going to have this upward-facing parabola y equals x squared. If I pick z equal to, 3, then this is going to be x squared minus 18. So it's going to take that parabola and drop it down by 18. But it's always going to be an upward-facing parabola. And we see that, right? If I pick any z value and fix it, I'm just getting that upward-facing parabola, upward-facing parabola, upward-facing parabola. Do the same thing, but now I'm going to pick a number for x and plug it in. If I make x equal to 3, that's going to be 9 minus 2y squared. That's an upside down parabola moved up 9. So if I spin it the other way around, they're all upside down parabolas. The parabola goes up as the x gets bigger, or I guess bigger in magnitude because I'm squaring it as well. So that would be like taking slices. We're going to call those level curves or slices later on. But right now what I'm just thinking about is, how am I getting this? So you can see here on this bottom face here, the footprint, you pick an x, you pick a y, you're in this 2D space, you pick an x, y, you're at a point, you plug it into the function, You square the x value minus 2 times square the y value, and you get a height. And that's where I put the point. That's where I put the dot. The z is the height, is the output for this surface. What about, here's another surface then. Graph the surface of z is equal to x. Now wait a minute. Where's the y? Is that a one, is that like a regular single dimensional 1D thing? No, that's still multidimensional. It's just that the y isn't in the formula. You can think of that as z is equal to 1x plus 0 times y if you want. So there's a y in there, but it's just multiplied by 0. So it doesn't matter what y is, the height is only determined by the x value. What would that look like? Well, we can switch this out. I'm in a program called dpgraph here. I can switch the formula out that I'm drawing and just make it z is equal to x. So that means that no matter what y is, the curve will stay the same. Oh. Yeah, it's just a bunch of lines. It's a plane. And that's because this is the curve z equals x. So pick a y, the line z equals x. Pick a y, the line z equals x. It's a flat plane. If I open it up, let's just, I know it wasn't in the notes there, but let's make it a linear combination. So 2 x's plus, 1 y. And what am I going to get? It's a linear, z, the height is a linear combination of the x coordinate and the y coordinate. I'm getting a plane. Linear combination, a plane. That's a little bit of foreshadowing. We're gonna learn about writing, how to create planes. Planes are like 3D lines. Our points then are described as, an x, a y, a z coordinate if I'm in 3D. We can of course go, and that's in R3, like if we graphed in like our regular, we were in R2, now we'll be in R3. And we graph that with a 3D axis. Our x coordinate, our y coordinate, and our z coordinate going up. We can still talk about range and domain then. So the domain is the input. The dimension of the domain has got to be, since we're talking about multivariable, there should be at least 2 input variables. So our range is, our domain is at least 2-dimensional. And our output is 1-dimensional. Output is always 1-dimensional. So in a 3D graph, I've got 2 dimensions for the input and 1 dimension for the output. 2 plus the 1, that's 3. That's why we're in 3D. Old-fashioned, or the calculus we were doing before this, single variable calculus, we had 1 dimension for the input and we had 1 dimension for the output. So it was a 2-dimensional graph, with just a straight parabola that I could draw on a piece of paper. If I add the dimension of the input, the domain, plus the 1-dimensional range, the output, I get the dimension of the space that the surface is in, Rn, that the shape is in. So we can still talk about range and domain, though, of those functions. So here's a question, an example. Find and sketch the domain of the function. So the height is given by the square root of x squared minus y divided by the ln, the natural log of y plus 3. Now there's a couple of things to think about here then. I can't divide by 0, and I can't take the square root of a negative number, and I can't take the ln of 0 or a negative number. So let's consider those things kind of each individual. So the thing under the square root sign, the x squared minus y, that's got to be greater than or equal to 0. That has to be true. I can't divide by 0, so the ln of 1 is 0, so y can't be equal to negative 2, because that would make you take the ln of 1, which is 0, and then you divide by 0. Also, you can't take the ln of 0 or a negative number, so y has to be strictly bigger then minus 3. So these are the sort of the checking the three things all has to be true. Anything that doesn't or that satisfies all of these three requirements is in the domain. It's a set, then it's in R2. If I was going to write this, you'd write something like the domain is all the set of the xy points such that, and then you just list all these three things. Let's do them in order. And you might put comma, x is an element of xy is an element of R2 or something like that. But anyway, that would be our domain. But I'm still like, that's kind of find the domain. I'm still looking at this and I don't see anything. It would be better to draw this domain. So let's make a sketch. Let's make a sketch of this domain. Okay, so x squared minus y has to be greater than or equal to 0. Where is it equal to 0? Well, on the parabola y is equal to x squared. So let's draw that. Well, okay, I'm in Microsoft. That's a terrible drawing. But anyway, that's y is equal to x squared. And we either want to be, on that graph is okay, because I can take the square root of negative number. I can take the square root of 0. So on this, the thing under the square root sign is 0. It's okay if the x is bigger, x squared is bigger than the y, so I want to be below that curve. So we're talking about below this curve. So on this curve and below this curve so far satisfies that first inequality. What about this inequality? Well, this one's easy. Y can't be equal to minus 2. So I'm going to put a dotted line at minus 2, and also y can't be equal to minus 3, so I'm going to put a dotted line at minus 3, and so now I want to be below or on this parabola, not equal to minus 2, but above and not on this y is equal to minus 3 line. So I'm shading in, can I do shading with a spray paint? I'm shading in this here, not the dotted line, and here, not the dotted line. So solid means I'm allowed to be on it, dotted means you can get right up next to it, close to it, infinitely close to it, but not on that line. So what I've shaded in here is the, on my really crummy paint drawing, is the domain, the 2D domain of the function. All right, this is a little bit like visually more clear than our set idea. What about the range of the function? Well, the range of the outputs. So because I can make y super close to minus 2, I can make the ln of this thing, the ln really close to 1, so I can almost divide by 0. So whatever this positive thing is up here, I can go to pick a, if I make y close to minus 2, this would be like x squared plus 2-ish. And so I can make x different and make this square root thing as big as I want, divided by almost close to 0. So I can make the z shoot off to infinity. Likewise, if I make y close to minus 2, but let's say minus 2.1, then I'm close to 1, so I'm close to dividing by 0. But I'm on the negative, the ln is of a negative, the ln is negative because my y plus 3 is a little bit less than 1. So now I can get all the negative numbers. Can I get 0? Yeah, sure. pick a y and make the x, like 4, and make x squared 2. So 2 squared minus 4, I can make this 0. Long story short, we didn't ask for the range of this, but I knew it would be one-dimensional. The range is all of the z values. The range is all of R. The domain is a subset of R2, and that's the subset that I tried to draw here. Let's do one more question then. Let's find the range of this function. Okay, so the range. Well, let's take a look. Sine can be, it's sine times the arctan. Sine can go all the way up to 1 and all the way down to minus 1. Arctan, the biggest arctan could ever be is pi over 2, and the smallest arctan could ever be is minus pi over 2. So you've got this piece here that goes, the biggest almost pi over 2, and the smallest almost minus pi over 2, multiplied by something that can get to 1 and to get to minus 1. So that means that the range, what w's can come out, is in between minus pi over 2 and plus pi over 2, but I'm going to go with the strict inequality, so they would be dotted lines there. If I would write this in interval notation, it would have the round brackets, because we never actually get to pi over 2, because the arctan approaches pi over 2 or negative pi over 2, but it never actually gets there. So there's our range of the function.